Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
We're very happy to have today John Lay from Harvard University. He's a postdoc candidate for this upcoming academic year, and he's going to be talking about machine learning for mechanism design.
All right, thanks. So I'm going to be talking about some work we've been doing that ties in machine learning methods to mechanism design. So here's just a brief outline for the talk. I'll start out with some background on mechanism design. Then I'll move to the machine learning side and talk about structural classification and support vector machines. And then in the third section, I'll tie together the structural classification with mechanism design. I'll move on to some experimental results and some more recent work that we've been doing on trying to make the training problem more tractable in our formulation. And then I'll end with some brief remarks on my overall research agenda. So to start off, one way we can think about mechanism design is that we're doing optimization, but the inputs to our optimization problem are private. And in particular, they're possessed by self-interested agents. So some practical examples of mechanism design. We can look at the FAA's problem of trying to allocate landing slots at congested airports. So here, the self-interested agents are the airlines, and the private information are the airline's values for different landing slots or combinations of landing slots. So similarly, we can look at the problem of the FCC trying to allocate wireless spectrum. So here, the self-interested agents are the cellular companies, and the private information is how much value the companies have for different portions of the spectrum. And the FCC's goal might be to try to maximize the total value of the spectrum, but they don't know the true values. So we need some way to get the companies to elicit these values. And then finally, in the university setting, you can think about course assignment as a mechanism design problem. So here, the self-interested agents are the students. They want to try to get the best course schedules possible. And the university is trying to get the students to simultaneously submit their preferences and also perform some optimization over the submitted preferences. So more concretely, we can look specifically at the landing slots example. So here we have 3 airlines, and these are their sort of private values for different landing slots at a given airport. So here we see that we also give values for combinations of landing slots. So these landing slots could exhibit complementarities, in which case if I get 2, if I get both landing slots, the total value is higher than the sum of the individuals. Now the mechanism asks each of the airlines for a report of their values. So here, American Airlines says, these are my values for the landing slots, and the other airlines also provide their values. So the mechanism operates on these reported values. So it doesn't know the private values. And the reported values could be different than the actual values. And what the mechanism does is it looks at these reported values and it computes 2 things. So the first thing it computes is an outcome. So it assigns the landing slots to airlines. And the second thing it computes is a payment for each airline. So in this talk, we're going to be looking at the setting of mechanism design with money. So we assume that we can use payments to incentivize the participants to report their information truthfully. You can also think about mechanism design without money, but that's going to be beyond the scope of this talk. So the main goal here is we're going to try to make it so that the mechanism does 2 things. We want this outcome to maximize some objective function. Right? So for the government, we might want to find an assignment that maximizes social welfare or the total value that these landing slots are creating. The second thing we want to do is that we want these reports to align with the true reports. So we're going to want to create the mechanism so that airlines are incentivized to tell us their true valuations. Yes?
Can you repeat, when do the payments have to be given? Is it when they apply for a slot, or is it once they get a slot? Does it depend on the slot that they get? Or?
Right. So I'm going to be looking at the setting where the payments are done after the reports. So you don't have to pay anything to submit your valuations. At the end, I'm going to compute two things. I'm going to compute the assignment and then how much you pay for whatever you get. You can also think about mechanisms where people are required to put up some amount of money in order to even participate in the mechanism. But in this setting, we're going to be looking at payments after the fact. So more formally in the talk, we're going to use V sub I to denote an agent's private information. So here V sub 1 might be an airline's values for all the different landing slots and combinations of landing slots. We're going to use omega to denote the space of possible outcomes. So in the landing slot example, this is an outcome will be an assignment of landing slots to airlines. We're going to use F to denote the outcome rule and T sub I to denote the payment rule. And as I mentioned, we'll want two things. We want that F has good performance with respect to some objective function. So here, we might want an outcome that maximizes total value or welfare. And then we want F and T to work together so that we have good incentive properties. In particular, typically we want that it's always in an agent's best interest to report its valuation truthfully. So here what we see is that this is the agent's value when reporting truthfully minus its payment. This is the agent's value when reporting something else, and its payment when reporting something else. And we want its value minus payment when it reports truthfully to be greater than its value minus payment under any other reports.
This seems like a good thing, but why is it actually important? If we get better social welfare out of some scheme that's not incentive compatible, why isn't that better?
Right. So so you can. There's sort of a couple answers to that question. So one answer is that suppose you have some mechanism that isn't or that isn't incentive compatible. So then now you have to start thinking about well, how will agents actually behave when they participate in this mechanism? So you need to start thinking about the equilibrium of whatever system you've created. So that's one thing. So in terms of analysis, it becomes harder to understand, to exactly predict what's going to happen in your mechanism, right? So depending on information, different agents might behave differently. Another advantage is that if you have incentive compatibility, then you're sort of you're not giving an advantage to more sophisticated agents. It's actually it's straightforward to participate in your mechanism, right? So if I'm one of these airlines, I know that the best thing I can do is to just tell you my true valuation. I don't have to go and think about, well, what are other agents' valuations and things like that.
So it makes life simpler for everybody.
Right.
Okay.
So as I mentioned, mechanism design is looking at this optimization problem when the inputs to the optimization are private. And so it's challenging because we have this simultaneous optimization over an outcome rule and a payment rule. They have to work together to create the right incentive properties. And so in terms of theory, we have good understandings of sort of simple settings, right? So if an agent's valuation can be described by a single parameter, then we have a good understanding of what mechanisms to use, what good mechanisms are. Or if the objective is welfare maximization, so if we want the outcome rule to maximize the total value, we can use the VCG mechanism. And that says that we'll select the outcome that maximizes total value, and the payment rule will be something that charges the externality that an agent is imposing on the system. And if you combine these two things, you get incentive compatibility. Now, one thing here is that we're assuming that this problem is computationally feasible, which in some cases it's not. So finding an allocation that maximizes welfare can be a computationally hard problem. And so things break down when you look at, say, algorithms that approximately maximize welfare. You can try that and use the same payment rule, but then that breaks the incentive properties that you have. So you really need this exact maximization here for incentives to work out exactly. in practice, things are typically more complicated. We have valuations that are multi-parameter. So in the landing slots example, airlines, their valuations aren't described by just a single number. They're described by these different numbers for different landing slots and combinations of landing slots. And also, we might have different objectives that are different than welfare maximization. So even if you think about the government might want to try to maximize welfare, but also preserve some minimum level of competition. So when we look at these different objective functions, it becomes less clear on the theory side in terms of what sort of mechanisms we should use. So the goal of this talk is to try to use more computational approaches to design mechanisms for these more complicated settings. So just as a couple of motivating examples, the one example where the theory doesn't give us an answer about what to do is the setting of multi-minded combinatorial auctions. So a combinatorial auction is a setting where we're auctioning off multiple items at the same time. And multi-minded just means that each agent is interested in specific subsets of items. So here, American Airlines is interested in this schedule and has value 5 million for this schedule. And this other schedule, it has 2 million for this schedule, and then $8 million for this schedule. So there's sort of these subsets of items that each agent's interested in, and they have a value for each subset of these items. Now let's suppose that our objective is to maximize welfare. So we can use the VCG mechanism, but even in this sort of restricted combinatorial auction setting, finding the welfare maximizing allocation is MP hard. So as I said, you could try to use the VCG payment rule with an outcome rule that approximately maximizes welfare, but that's no longer incentive compatible. So the question here is, well, what mechanism should we use if we're operating in this setting? As a second motivating example, let's suppose we're looking at a landing slot example where we're at a rural airport. So there's only three slots a day, and the government wants to make sure that there's competition at this rural airport, so it wants to say that each airline should be allocated exactly one slot. So what we're looking for is an assignment from airlines to landing slots. And the objective is we're going to try to maximize the minimum value obtained by any airline. So we're going to look for the assignment that maximizes this minimum value, which we term the egalitarian assignment. So in this setting, VCG doesn't apply, but for a different reason. The objective is no longer welfare maximization. We're not summing over the values of all the airlines. We're trying to maximize the minimum value obtained by any airline. And so in this setting, we can again ask the question about what mechanism should we use if we're looking at trying to use this, looking at this objective function. Okay. So here's a high-level view of the computational approach that we're going to take. So we assume that we're given an outcome rule. So we're given some procedure where if I give you reported valuations, I get the outcome that's computed. And I also assume that I'm given a distribution on the possible values of the agents. Now we're going to apply machine learning methods to learn a payment rule that works well with this outcome rule. So one caveat is that we need this distribution on values here. But the advantage is that we'll be able to handle these outcome rules that you might not be able to specify analytically. So they might just be some heuristic algorithm that finds an allocation with good welfare. So we're going to treat the outcome rule as a black box. We'll also be able to handle the case where there are certain outcome rules where you just can't make them incentive compatible. There are no payment rules that will make certain outcome rules incentive compatible. So we're going to define in a specific way, sort of relaxing away from exact incentive compatibility. So I'll get into the exact definition later on, but we're going to try to learn something that has good incentive properties but may not be exactly incentive compatible. And by drawing these connections between machine learning and mechanism design, we'll be able to leverage the advancements that are ongoing on the statistical machine learning side of things. Yes.
Do you assume that the distribution on V is the distribution of values from your agents? Or is this a more of an analytical?
Right. So we basically have to assume that if we run our mechanism, the agent's valuations are being drawn from this distribution, and that we know that distribution. So yeah, so you have interesting questions about where do you get this distribution and things like that. But we're going to assume this in our work. Yes.
Do you generally need that, or do you mainly need that for objective functions that involve some expectations? And some objective functions have these ex post goals where the distribution might not matter.
Right. So it is something that we will need in order to apply this machine learning type approach. So ultimately, what this ends up doing for us is this will let us generate training data in the machine learning sense. So we will need it regardless of the exact form of the outcome rule. Okay. So there has been other work that takes computational approaches to mechanism design. So in particular, there's work called automated mechanism design, where they frame the problem of mechanism design in terms of an optimization problem where you're optimizing over both the outcome rule and the payment rule simultaneously. So the main difference here is that we're assuming that you give me an outcome rule, and I'm just trying to learn a payment that works well with it. So Brendan has some work that looks at taking any approximation algorithm and turning it into a Bayesian incentive compatible algorithm with the same approximation factor. So the main difference here is that the objective function here is welfare. And we're sort of looking at cases where the objective function is coming through via the outcome rule that you give us. There's work that looks at learning voting rules from examples. So given examples of how a voting rule decided the outcome of an election, trying to recover the form of that voting rule. But this work doesn't really look at incentives at all. It's a pure sort of machine learning perspective on the problem. There's also work that looks at using kernel methods for pricing and clearing combinatorial auctions. So in terms of technique, we also use kernel methods from machine learning, but the problems that we're trying to solve are very different. We're looking at a mechanism design problem, whereas here they're looking at given an instance of a combinatorial auction, I want to find market clearing prices. So the techniques share similarities, but the targets and settings are very different. So just some more details on exactly what our computational approach involves. So we assume that we have this distribution on values. We're going to sample a number of values. So given this distribution, we'll sample m possible valuation profiles. So here, v superscript 1, that's a value for each agent. So this is like a report, an entire set of reports for the agents. Now we assume that we're given an outcome rule. So we're going to apply the outcome rule to each of these valuation profiles that we've sampled. So we'll get a valuation profile outcome. We'll get a pair of valuation profile outcome. And we'll have all of these pairs. Now we're going to treat this as training data in some machine learning problem. And we're going to try to learn this mapping from valuation profile to outcome. So ultimately, we view this as training data. We're trying to solve this prediction problem of, given a valuation profile, what's the outcome that this outcome rule would have computed? And then from the form of this learned classifier, we'll back out a payment rule that works well with the outcome rule that we're given. So I'll get into more specifics later, but this is sort of the high-level view.
So
yes?
It's not just that you're trying to get inside the black box, but you want something with a particular form that will let you construct the payment rule.
Yes, exactly. So you can think of it as, well, it's kind of, one thing people ask is, well, we already know what this outcome rule is. Why are we solving this sort of prediction problem to figure out the outcome rule? Well, the answer is that when we do this learning, we're going to restrict the form of the thing that we can learn, and then we're going to get the payment rule from that restricted form. And if that restricted form allows us to predict the actual outcome rule well, then we'll have something that has good incentive properties. If it doesn't, then we won't.
So it seems like you're also assuming that you have access to the distribution only as by sampling, because if you
Right.
actually knew the distribution, you would not need the sampling itself. You could just solve this approximation problem of finding something close to f which has the form that you want.
Right.
You're also assuming that your access to the distribution is through sampling.
Right. Yeah. We're assuming that basically, yeah, we can ask this black box, give me a sample from the true distribution. Okay. So in the second part of the talk, I'm going to talk briefly about the machine learning side of things, just give you enough background so that we can have enough information to draw these connections that we're trying to make. So structural classification is the problem of learning a mapping from some input space to some structured output space Y, where Y has some structure in that it can have a large number of elements, but it has some structure. So the easiest way to see this is through a couple of examples. So in part of speech tagging, we're trying to, given a sentence, we're trying to figure out the parse tree for that sentence. So in this case, the output Y is going to will be the space of all possible parse trees for a given sentence. You can think about OCR in the context of not just a single character, but an entire word. And so here, we're given an image of a word, and we're trying to output exactly what word is in the image. So in both of these cases, the output space is large. Here we have parse trees, and here we have possible words, but they're also structured, right? So here, we're going to only be looking at valid parse trees, and here maybe we only want to output words that are in some sort of dictionary. So one way to solve these structural classification problems is the following. So we assume that we have some training data, x superscript k and y superscript k. So we have some inputs that we're trying to learn from, and we're going to learn a discriminant function. So for every given input and every possible output, we'll learn something that assigns a score to that pair. The prediction then is, if I give you some input, the prediction will be the output that has the highest score, right? So I have this discriminant function that says, given this input-output pair, how well do they fit together? And to make prediction, I'll just say that I'll output the target that has the highest score. So in particular, what is the form of this discriminant function? It's going to be the dot product between some weight vector and some feature vector. So the feature vector is something that we specify. So this encodes our domain knowledge. It combines the input with a given output. And the weight vector is what's ultimately learned by the framework, right? So we give you the feature vector, we give you some training data, and the framework should output a weight vector, which will then define your discriminant function and give you a classifier. So now, given an input, I can run my discriminant function over all possible outputs and tell you my prediction. And as is typical in machine learning, we'll want to avoid overfitting, which means that we are trying to learn from this training data, but ultimately what we care about is performance on data we haven't seen before. We don't actually care about how well we do on the specific training data. So one way to avoid overfitting is by using the idea of maximizing margin. So if you look at this optimization problem, what this is saying is that we want the scores for the correct output. So these are our training data pairs. We want the score for the correct output to be higher than the score of any other possible output. So we want our classifier to be correct. But not only that, we want the two to be separated, right? So we want the score of the correct target to be much higher than the scores of other targets. And so if we can try to maximize this, we can avoid overfitting. So as an example of what we mean here by margin, suppose we just have two classes of data. The input can be either negative or positive. So we're going to define the margin as the distance from the boundary to the closest point on either side. So in this case, if this were our decision boundary, everything to the left is negative, everything to the right is positive, our margin is going to be the distance from this boundary to the closest point on either side. Now what you see is that if we rotate this boundary, we can make the margin larger. So increasingly, if we rotate it this way, the margin becomes slightly larger. And then if we rotate it even more, the margin increases even more. And the insight we're going to use is that we prefer boundaries like this to boundaries like this. We want boundaries that have higher margin. And the reason is that, and this will help us avoid the overfitting problem. And one intuition for that is that we're sort of making less assumptions about the unseen data when we use this boundary versus this boundary. Like if you look at this boundary, we're implicitly assuming that the points up here are minus and the points down here are plus. But here we're not making, we're making fewer assumptions about the data. And by doing that, we'll be able to avoid overfitting. So it turns out that this optimization problem is exactly equivalent to maximizing margin. And I won't go into the details of that, but if you look, there's one problem with this formulation, which is that it might be infeasible, right? So there might not be any weight vector that always gives the correct targets higher scores than all the other targets. So one thing we'll want to do is we'll just want to introduce errors. You can make errors. You might not always assign the highest score to the correct target, but we'll penalize those errors. So if you want to make errors, you can increase the slack variable, but we'll penalize the slack variable in the objective function. And then this parameter controls the trade-off between sort of how well you're fitting the data and how large of a margin you're getting. And so this is something that we'll have to tune when we actually run experiments. So one thing to keep in mind is that if you look at these constraints, there's actually a large number of constraints. So I said Y could be this large space of possible parse trees or words in a dictionary. And we're saying that we have to have one of these constraints for every possible Y. And so if you want to be able to solve this in a computationally tractable manner, when Y is large, you'll need some sort of separation oracle. You'll need some efficient way of sort of finding constraints that are currently violated and dealing with those. So I'll get into that a little later. But this sort of right now it's not clear that this training problem can be solved in a very efficient way because of this large number of constraints. So the main takeaway from this section of the talk is that we have existing methods for predicting large structured output spaces. And in particular, these max margin approaches have been successful. So on the two examples that I mentioned, max margin approaches are able to improve upon the state of the art by significant percentages. So now I'm going to talk about our main contribution, which is tying in these machine learning methods to the mechanism design problem. So just as a reminder, our goal is that we're given an outcome rule F, and we're trying to learn a payment rule T that has good incentive properties. Now for the rest of the talk, I'm going to make a few simplifying assumptions. The first is that there are no externalities. So what this means is that an agent's value for an outcome only depends on the part of the outcome it receives. So American Airlines, they only care about the landing slots they receive. They don't care about sort of the allocation of the rest of the landing slots. So that's definitely a simplifying assumption, but it's something that'll make the presentation easier. We also assume that the outcome rule we're given is agent symmetric. So it is a black box, but it's not treating any of the agents in a special way. So if we renamed the agents and reran things, we'd get the same outcome. If we make these two assumptions, we can look at just a single agent classification problem. Instead of predicting the entire outcome, we can just look at agent 1 and try to predict the outcome to agent 1. We'll learn a payment rule for agent 1, and then we can apply the payment rule to all of the other agents as well. Our methods do extend to the case where if you don't want to make these assumptions, but it'll be easier to think about for the rest of the talk. We're looking at this single agent classification problem that will end up solving the problem we're trying to solve. but we'll be focusing on agent 1 in a special way. Yes.
I'm not sure how, I mean, the fact that you assume is symmetric, how does it mean that you can do the prediction separately? For instance, if f is maximum over all agents or minimum over all agents, then it doesn't only depend on the value of any one agent, even though it's symmetric.
Right. So we're not just looking. So we're sort of still looking at we're looking at f. So f is given all of the values, and it's going to compute some outcome. We're just going to look at the outcome for agent 1. So we're still looking at all the values. We're just looking at a specific part of the outcome. So originally we were saying, given the values, I want to predict the entire outcome.
You also need to assume that the distribution is
Symmetric, right? Yeah, that's right.
So I'm confused. Your landing slot examples, were those agents symmetric?
So I guess you don't. Okay, so you don't actually. So the answer to your question is, you can't tell if they're symmetric. They could have been drawn from the same distribution, right? Or they might be drawn from the same distribution. But in general, we don't need that. We don't need the distribution to be symmetric. You can run this problem for every agent, right? For every agent, I want to predict your outcome. For the second agent, I want to predict your outcome. We do need no externalities for that. We don't need agent symmetry for that. The problem, if you don't have agent symmetry, then you need to do a learning. If you don't have agent symmetry or you don't have the symmetry in the distribution, you have to do a separate learning for every agent. If you have both of those, you can just learn for one agent and apply it. But you can, the methods I present, it's not going to, you can think of it as sort of, I could apply this to every agent. And it'll solve the asymmetry in the distribution or asymmetry in the outcome rule. So we're going to use omega to denote agent 1's allocation and just drop this omega 1 just to declutter the notation. Okay. So here's sort of a well-known characterization of incentive-compatible mechanisms, but it'll turn out to be very useful in our setting. So let's fix the valuations of other agents, and let's see what American Airlines can do by varying its report. All right, so it could report its true value, v sub 1. That'll give it some outcome and charge it some payment. It could report some other valuation v1 prime. It'll get some outcome, maybe it's the same, and it'll get some other payment. Now, you can go through this exercise for all different possible reports, and basically, by changing your report, you can change your outcome and change your payment. So the first observation is that if your mechanism is incentive compatible, these two payments have to be the same, right? So it can't be the case that you can report two different things, get the same outcome, and be charged different things. Because in this example, if my true value is v1, then I'll just report v1 prime. I get the same outcome, and I'm charged less. So this payment up here has to be the same. Let's just say they're both 4 million. So that's the first observation. So the second observation is that now we basically have a way, by changing our report, to get different outcomes. For every outcome, there's a fixed payment, right? We said the payments can't differ for a given outcome. So essentially what an agent's deciding is like, okay, this is my valuation. I can get all these different outcomes, these different outcome payment pairs. So it's basically thinking, well, what should I report to get the outcome payment pair that maximizes my utility? So now if the mechanism is incentive compatible, when the agent reports v sub 1, the outcome payment pair that I output has to be the outcome payment pair that maximizes agent 1's utility when its valuation is v sub 1. Right? So suppose not. Suppose that when the agent's value is v sub 1, it actually prefers this outcome payment pair. Well, then it'll report v1 double prime instead of v1. And your mechanism is not going to be incentive compatible. So the main takeaway is that if we know, suppose that we knew for this outcome the payment's 4 million, and this outcome the payment is 8 million. Now when an agent makes a report, all we have to do is we have to pick the outcome and payment pair that maximizes that agent's utility under its report. Right? We have these, I can give you this outcome for this payment, this outcome for this payment, and you're telling me this is your valuation function. For F to be incentive compatible, I have to give you the outcome and payment pair that maximizes your utility. So in some sense, you can think of this payment function, so this payment that maps an outcome to a payment, you can think of that as fully determining your outcome rule if your mechanism is incentive compatible. Like if I know the payments I'm charging, then I know the outcomes that I have to give you. So in some sense, you can think of this payment rule as a classifier for the outcome rule. And so what we're going to try to do is basically reverse this, right? So we're saying that if I knew the payment rule, I could tell you what the outcome rule would be if you were working with an incentive compatible mechanism. Well, the problem we're trying to solve is we're given the outcome rule, and we're trying to find a payment rule. So we're going to try to say that if we have an outcome rule, we're going to try to say that if I can learn something that predicts your outcome rule well, then I'll have a payment rule with good incentive properties. So we're basically trying to reverse this observation that the payment rule pins down the outcome rule when you're incentive compatible. So as I said, we're trying to learn this predictor. We're trying to learn a predictor for this outcome rule that maps valuations to outcomes for agent 1. We're going to use the structural classification ideas we saw before, and we're going to try to learn an admissible discriminant function. So what that means is we're going to learn a discriminant function that has a particular form. So the discriminant function will take the valuation profile and a possible outcome that agent 1 could obtain and assign some score to that. We're going to say the discriminant function has to have the following form. It has to be decomposed as agent 1's value for the outcome minus this term on the right. And this term on the right, we're going to say it can't depend on agent 1's report. So the intuition here is that it can depend on the outcome, but for the same outcome, this term on the right shouldn't depend on agent 1's report. And that's sort of the previous slide we saw that the payment for an outcome shouldn't change if the outcome shouldn't change depending on an agent's report. For a given outcome, the payment has to be the same. And then, so this is something that we know. This is the feature map that we specify. This W is what we're learning in our framework. And then the payment rule that we use will just be this term on the right. So we're going to learn this weight vector that parameterizes this discriminant function, and then the payment rule that we end up using will just be the right-hand side of this discriminant function. And the claim that we want to make is that if you learn a classifier of this form and it's an accurate predictor of the outcome rule F, then this payment rule that we back out will be a payment rule that has good incentive properties. And sort of orthogonal to that, the payment rule will also be agent independent, right? So the payments will depend on the outcome. So if you're an agent, you can change your outcome and change your payment, but for the same outcome, you can't change the payment. So sort of local changes in your report don't make any difference unless they change the entire allocation that you're given. So this, in some sense, gives us local stability of our payment rule. So if you think about the auction setting, like the second price payment rule has this local stability property, but the first price auction doesn't, because you can keep winning but lower your price in a first price auction. So we have theorems that make the relationship precise. So the first theorem is that if our learned classifier is exact, then if we pair the outcome rule we're given with the learned payment rule, that pair is incentive compatible. So the proof is pretty simple. So suppose that when agent 1 reports truthfully, the outcome is omega. And when agent 1 reports something else, reports v1 prime, the outcome is omega prime. We want to show that under the payment rule that we learned, the agent's utility under outcome omega and reporting its true valuation is at least its utility when reporting v1 prime. So the first step is to notice that this is the exact form of the discriminant function that we've learned. The second step is to use the fact that our classifier is exact. So exact means that the score for the true outcome omega should be greater than, should be at least the score for any other outcome omega prime. And then we'll just reverse the definition of the discriminant function. And this is the right-hand side that we were trying to show before. So basically, this proof just relies on the way we forced our discriminant function to have this form. And if the discriminant function is exact, then we get this relationship. The score for outcome omega is at least the score for outcome omega prime. Yes?
This result seems to be distribution free, is that right?
So it's not distribution free. We need the classifier to be exact, so it actually predicts the correct outcome for every possible report. Right. So yeah.
So this is true for all v minus
Right.
minus I, and so.
Right. Yeah. So you can think about it as distribution free, or it in some sense has to hold for every distribution. The second theorem that we have just works in the opposite direction. So it says that if you have an incentive-compatible outcome rule, then there exists an exact admissible classifier for some feature mapping. So I didn't get into too much details about exactly what this feature mapping is, but this is just saying that if you have an incentive-compatible outcome rule, if you have a very rich sort of family of functions that you're learning over, you'll be able to learn an exact classifier. So I won't go into the details of this theorem, but I want to get to the third theorem. So the first two theorems look at cases where we have exact incentive compatibility and exact classification. So here we're going to look at cases where the classification isn't exact, but it's sort of tries to minimize some sort of error function. So in particular, let's define the error of a classifier as being the difference between the value of the discriminant function on the thing that the classifier predicts minus the value of the discriminant function on the true target. Right? So if we're predicting the true target, then this error will be 0. These two terms will be the same, but otherwise this term will be positive. If we're making an incorrect prediction, there'll be a difference between the score of the prediction and the score of the target that we're trying to predict. On the mechanism design side, we can look at regret, which we can say is the utility of an agent for its best report. So it could report anything. What's the utility of its best report minus its utility for reporting truthfully? And the theorem is that if we have an admissible classifier that minimizes this generalization error, so this error that's dependent on the discriminant function, then we'll find a rule that minimizes expected regret. The payment rule that we learn will minimize expected regret. So even when you don't have exact classification, if you minimize this error function, then you'll recover a payment rule that minimizes this regret, which quantifies how much an agent can gain by misreporting. And again, we still learn payments that are agent independent, which has this nice local stability property. And as I mentioned, we'll be able to relax away from exact incentive compatibility in this sort of specific way of minimizing expected regret. So just as a review, we've given a method to learn a payment rule for any outcome rule f. And this allows the mechanism designer to focus on the outcome rule. So you give me the outcome rule as a black box, in addition to some way to sample the distribution. And this computational approach will give you a payment rule that has some reasonable properties. And we move smoothly away from exact incentive compatibility. Okay, so I'll briefly talk. Yeah, Gabe.
So I was going to ask now after seeing your last slide about sort of the perspective you're taking. So you're really not thinking about a designer who is given the black box and has to come up with payment, but you're trying to simplify their task in designing a mechanism by saying you can design just the outcome rule instead of designing both parts, right? So is there some way we can think about? I mean, so if I'm designing an outcome rule, for me to know that there is going to be a payment rule that makes it, say, approximately incentive compatible, and my outcome rule has to satisfy certain property, right? It has to be monotone.
Right.
So, and then once I've done that, coming up with once I've got an outcome rule to satisfy that, then coming up with the right payment rule is pretty straightforward. So is there some way to think about situations where sort of having these kinds of results will where it's easier to design just the outcome rule than to design both at once?
Right. So one thing is, I think it's true that in sort of simple domains, recovering the payment rule, so if you have these monotonicity properties, you can recover the payment rule easily. I'm not sure if that's true in sort of we know what the payment rule should look like, but it's still not clear exactly what it is. Is that right? It satisfies certain properties.
Right, but I guess also it seems like the reasons why it's hard to actually figure out what the payment rule should be are also the reasons why it's hard to figure out whether there even is a payment rule that makes your outcome rule, right? So the incentive compatible, right? So I'm wondering whether there are situations where designing an outcome rule where we think that good incentive properties exist, but we can't actually find the payment rule directly, whether that's actually any easier than just coming up with both at once.
Or to put it another way,
Right.
perhaps, does this scheme give me any guidance in designing the outcome rule?
Right. So I don't think it gives you.
I pick a really crappy outcome rule,
Right.
then you'll still produce a payment
Yeah,
rule.
I'll still produce a
So
payment
how
rule.
do I know how good a job I did?
Right. No, I think that's a good question. I don't think this gives you any guidance beyond what's already known in the economics literature about properties like monotonicity of your outcome rule and things like that.
Well, if I understand correctly,
Right.
at least gives you an experimental framework, so I could develop.
Right,
one
that's
thing.
true.
I could say I have some heuristics. I don't know how it works. I could design a bunch of outcome rules, and I could run.
You
some
could look at
experiments
regret
and see.
and
Okay,
things
well,
like
I get a good classifier
Right.
here, but not there.
Right.
Maybe this one seems
That's
to be
true.
good.
So you assume the distribution, but I didn't see, when you didn't talk about it, the dependence of your results on the distribution. I mean, the result that you did give was dependent maybe on the support of the distribution because it really had to hold
Right.
all of for any other distribution on the same support. So is there any result that depends on the actual distribution?
Yeah. So I didn't exactly write out what I mean by expected regret here, but this will depend on the distribution. So this is going to integrate over the distribution that we're given.
Just another question. The distribution is over the true values, right?
Right.
So you basically assume that there is a way to access the actual true value of the agents.
Right.
So you kind of contradict the whole assumption that you don't know their true values.
Right. So there's, I guess there's a difference between knowing their true values in every instance and knowing the distribution that their values are being drawn from.
Which you do by sampling.
Right. So there is definitely yeah.
Actually know it at a specific instance.
I mean it's true. There's definitely this problem of this question of where do you get the distribution from? Like you could argue that you sort of get the distribution from the past where you've maybe run some incentive compatible mechanism that doesn't have good properties. You can imagine doing that. But in general, when we're thinking about, I mean, it's a sort of knowing the distribution is a pretty standard assumption in the literature on designing Bayesian incentive compatible mechanisms. But no, I agree. There is this question about where does this distribution come from? Brendan? Oh, sorry.
Could I use this scheme? Suppose I'm contemplating some parameterized family of outcome rules. Could I use this scheme? Could I wrap this scheme in another layer of machine learning and learn the parameters for the outcome rules?
Yeah, presumably you can, because out of this thing you get some measure of how well you're doing. Right. And there are lots of methods for sort of doing local search over parameter spaces and things like that. So that's definitely an interesting direction to think about. Okay, so we have 5 minutes left, so I will quickly go through the experimental results. So we implemented this for the two settings that I discussed earlier, the multi-minded combinatorial auction setting and this egalitarian assignment setting. So the multi-minded combinatorial auction setting, we use an outcome rule that is a greedy algorithm that tries to maximize welfare. So it's not going to exactly maximize welfare. It does so approximately. The egalitarian assignment setting, we look at this objective where we maximize the minimum value that any airline receives. In both settings, we use what's called an RBF kernel. So what that does is that that maps this feature space that we're learning over into a highly nonlinear feature space. So it allows us to learn over very complicated payment rules, even though we're sort of specifying something that's simple. So this is a standard thing that's used in machine learning. The benchmark we use will be these VCG-based rules. So what we mean by VCG-based rules is basically we measure the externality that's being imposed by agent 1. So I'll go through this very quickly. The externality of American Airlines will just be how much value do the other airlines receive when American Airlines is around? And then if we removed American Airlines, how much more value do the airlines receive? So here the payment will be 11 million, which is here, minus the 7 million, which is here. So American Airlines pays $4 million. Now this rule is going to be this payment rule is incentive compatible if your outcome rule exactly maximizes welfare, but it's not incentive compatible in either of our two settings. So here we're looking at the regret of the payment rule that we've learned versus the regret of this VCG-based rule for the two different settings. So what we see here is that in the multi-minded combinatorial auction setting, we're learning a payment rule that has regret that's similar to this VCG-based rule. And in the egalitarian assignment setting, we're learning something that has significantly better regret. And so one reason why this might be true is that here we're still trying to maximize welfare, so maybe this externality-based rule is still doing something pretty reasonable. But here the outcome rule is really not maximizing welfare. It's doing this maximizing this egalitarian objective, and this VCG idea seems to break down a bit here. Another thing I wanted to note is that in the combinatorial auction setting, it's actually computationally intensive to learn this weight vector W. So if you remember, we have all these constraints. So we have a constraint for every possible element of the set Y. So in combinatorial auctions, that's going to be every bundle of items that agent 1 could have received. So if you have n items, you're going to have an exponential number of constraints. So training is a bottleneck here. And the last section of the talk was going to, in the last section of the talk, I wanted to talk about sort of overcoming this training problem. So I'll just give a very brief overview and then conclude. So right, when we're looking at combinatorial auctions, we have an exponential number of these constraints in our optimization problem. And what we really need is an efficient separation oracle. We want something that picks out the element, the subset of items, maximizes over this exponentially large set, but does so in an efficient way. So it turns out that we can do this if we consider a class of valuations which in the literature, which has been studied in the literature by a couple of papers. And this is a valuation that's graphical in nature. So on each node, we have the items, and then we have edges or hyperedges between items. And the edges and hyperedges say that if I have both of these items, I get a $1 million bonus. So this structure is completely additive. So if I give you just 9 a.m., you get $2 million. If I give you both 9 a.m. and 11 a.m., you get 2 million, 3 million, plus 1 million. If I gave you all of these items, then you would get all of the numbers in this graph. So if you look, so we have a way that if you work with valuations of this type, the training problem is still, you still have an exponential number of constraints. An agent can still receive any subset of items, but we can solve that maximization problem tractably. So we can have much more efficient training. So I won't go into the details of that, but I'm happy to talk about it later if anyone's interested. And so I'll summarize this part of the talk. We've drawn a relationship between incentive-compatible mechanisms and structural classification. We've said that a good predictor for the outcome rule gives you an approximately incentive-compatible payment rule. And we've applied this to multi-parameter settings and settings where the objective function is complicated and maybe not welfare maximization. In general, I'm interested in work sort of at the intersection of machine learning, optimization, and mechanism design. I've done some work on looking at the cake cutting problem and looking at both incentives in cake cutting and extensions to cake cutting that consider trying to optimize welfare in addition to fairness, which is typically studied in cake cutting. I've done some work on this mechanism design theory, trying to understand can we have truthfulness and fairness in combinatorial auctions, and more recently looking at the design of optimal auctions where agents can choose whether or not they want to reveal their identities to the system. And then finally, I've done work on computational mechanism design, which includes this work and also some work on taking branch and bound search and trying to use it for the purposes of mechanism design by designing a procedure that takes your branch and bound search and turns it into a monotone search procedure. I've been very fortunate to collaborate with a number of people during my time at Harvard, and I just want to especially thank my advisor, David Parks. And thank everyone for coming.
I have a question. I'm not sure it's really very good, but I guess a question about the general setting of using payments to get incentive-compatible results.
Okay.
It seems like this undermines the basic thing that you want to get by some sort of objective. For instance, the objective is to be egalitarian so that everyone gets a minimum of something, but then you ask them to pay for it, which means that they actually get less than that. So it's not a question really directed at you. It's just a general question of this sort of way of solving the problem of truthfulness.
Right.
Doesn't it undermine the objective that you're trying to achieve?
Right. So I think it depends a little bit on your objective. So if you're looking at the egalitarian objective, I think that's a very valid critique. If you look at social welfare, I think the critique, social welfare, ultimately, what does the government want, right? The government wants these items to go to people who value them the most. They don't actually care about the exact utility of the companies that, they want to maximize value, right? They don't care about sort of value minus payment, which is the utility that these companies are receiving. So I think to your question, there are certain objectives where payments might not be as natural. So this egalitarian objective, payments might not really be the natural thing to do. I mean, we looked at it here because it's this interesting setting where we have something that really isn't welfare maximization, and we want to see how well things worked. But you're right that in practice, it might not make sense to combine like egalitarian concerns with payments if you're really caring about fairness. Like much of the K-cutting literature doesn't use payments at all.
I think we're out of time.
Okay.
If you want to take questions, I'll be around.
Yeah, I'll be around.